Nevím, ahoj, ahoj. Jsem jenom to klikal a všechno fungovalo, takže asi to koukám, že nemáš tam nic jako utončí taky. A jak si to zkoušel, takže... Budete mít time. Countdown. Předpokládám chtít používat prezentér, takže je k dispozici. Co jsou online, tak to je nám. tady všichni z naší komise. Vlastně chybí asi Táňa. A ta říkala, že možná nedorazíme, takže...
Už tady sami vedeme schopně.
Ale tak máme 9:01. Asi budeme se začít. Já bych jenom řekl ty úvodní slovo anglicky, protože máme tady jednoho ze soutěžících, který je, předpokládám, že nemluví česky, Marwan. So I will say just a couple of words in English. I hope, Marwan, that you can hear us. It worked before, so hopefully it's still working now. I would like to welcome you here, this third annual Best Junior Paper Award competition. So I'm glad that we got 7 contestants. Actually, it's quite difficult to make any predictions based only on 3 years, because that's how long our award is sort of working or functioning. But there are 2 developments. One of them is, I would say, negative. One of them is positive. So let me start with the negative one, is that we are not getting more and more contestants, unfortunately. We're actually getting less. So we have 1 less than last year, when there were 7 of you. Unfortunately, today one of you has withdrawn, which is Tomáš Gerbesky from my former PhD student, and so it's completely my fault, I would say. But he has withdrawn, unfortunately, so we have only 6 contestants. And we will first start with those 2 who are online, and then we will continue on with the remaining 4 who are unfortunately present here, and they will give their presentation. So, the positive one, the positive development is that we are now today, this year, we have all the papers that were sent to this competition. They are journal papers, which is hopefully this trend will continue on also in the future. And first of all, I want to say that, and the contestants, they know the rules. They each will have exactly 15 minutes. Here's a countdown, so they can watch how the time is going down to 0 from 15, and then they will have to stop. And then we have 5, maybe more minutes, depends on how many questions our board will have. And I'm glad that this year there are all 8 of us, and who will then decide at the end who will get the awards. So let me start. First I will ask Marwan Handa. So can you hear us very well? Fine. So please share your screen, and I will, at this moment, let me close that so it will not disturb us. And all right, you are not going to see my countdown, but anyway, I will stand up 5 minutes before your end. So please start.
Okay. So thank you very much. So today I will present a joint work I did with Marek Tiborec and Michal Kočvara, where the main context is solving some problems in structural engineering within the framework of polynomial optimization and the moment sum of square hierarchies. And here in this work we focus on exploiting a special instance of sparsity while using this moment sum of squares hierarchies, which called term sparsity. And we will show how numerically these techniques can reduce efficiently and drastically the computational time. So the frame structure consists of interconnected beams via joints. They are widely used in civil engineering and mechanical engineering. And here, an example of how to model this kind of problems. which we consider design base made of elements which are potential cross-sections areas. So it's represented by a graph, and in this graph, some nodes there is some boundary condition, mainly you fix somehow, and on some nodes there you apply some forces. And the task is to select which cross-sections areas to keep, and also what are the thickness of these cross-sections areas, while respecting some physical conditions, of physical constraints of the structures. And one of the two problems I will talk about is the compliance minimization problem. And the compliance actually measures how flexible the structure is when it's when you apply some forces on it. And minimizing it, it's like to see how stiffer will be the final design, which here we denote by C, and A is the cross-sections areas, and here these PSD conditions, actually it encodes the equilibrium state coming from the equilibrium equation, which of course you do some transformation via the Schur complement lemma to have it in this format. And here it's a constraint on the overall weight of the structure, so you don't want the overall weight to exceed some threshold, and you want the cross-sections areas to be positive. And of course, here the stiffness matrix, actually the polynomial nature of the problem comes from here, is that the stiffness matrix depends polynomially on the cross-sections areas. And the second problem is the weight minimization problem. So here you want to minimize the overall weights of the structure, and mathematically it's just you change this, what was constrained here, it becomes the objective function, and of course you restrict the compliance to not exceed some threshold. So both are polynomials, so bringing this to general context of polynomial optimization. So here we denote by BD the standard basis of a given ring of polynomials. So I overline this basis because we will use it in the following for the term sparsity. And just to give an example, so for example, if you take any polynomial, you can always write it as a linear product by a vector and appropriate degree for this standard basis. And for polynomial matrices, it's the same. You can always write it in function of this basis. So in general, polynomial optimization problems are very hard to solve globally because of their high non-convexity nature. And solving them with the classical nonlinear programming algorithms not only not give you necessarily the global optimum, but also even if you reach a global optimum, you are not sure if you are reaching the global optimum. So there is no certificates in general. And there is the only established tool so far is the Lasser moment sum of square hierarchies, which was introduced by Jean-Bernard Lasser in 2001. And here I will just give a highlight how it works. So basically you choose, so you linearize your polynomial problem this way. So you multiply your, one part you multiply your constraint by this product of bases, and which you add these two additional constraints, which are, of course, they are like, after this product, they become matrices. And then you apply this linearization operator Ly, which actually how it works is just at each polynomial, it acts on the monomials. So at each monomials, it's transformed to just a real number. So it do this for all the monomials present in the problem, and thus what you obtain here is an SDP problem. And of course you solve this, so by noting this matrix by this, which we call the localizing matrix, and this one is the moment matrix, but we will just call them the moments matrices. Under some Hildas option you can obtain, like, more you increase this R, which we call the relaxation order, more you will tighten the lower bound. And of course, we have a result about asymptotic convergence when R goes to infinity. But in practice, normally it's converged generically. Means like after just few relaxation, typically 3 or 4, you have already convergence, and you can test the global convergence via these conditions we call flatness conditions. It's when the moments matrix become flat after a certain moment. And this condition you can apply it at any kind of problem, but some problems you can also derive some specific conditions or some specific certificates, but it's really problem specific. So I have this example here of the feasible set of this problem, which is a very small problem of weight minimization, which is written this way. And here it's at relaxation 1 and here at relaxation 2. So what is in solid here is the feasible set of this problem here, and what is around is the feasible set of its first relaxation. So here you can see that there is 2 points, and the yellow one represents the global optimum of this one, and the red one is the global optimum of its relaxation. And you can see that this consists the lower bound for this, and for the relaxation 2, the feasible set is tightened a little bit, and then both global optimum they just coincide at 1 point, which is in the red dot here. So the moment sum of square, it's very efficient, but the problem is it becomes really intractable when one has to increase the relaxation order for problems that need higher relaxation degree to converge, or for problems that have many variables. So usually what we do is we have to exploit sparsity when we want to solve bigger instances of polynomial optimization problems. And in literature there exist many kind of sparsity techniques, like correlative sparsity or structural sparsity when you deal with polynomial metrics inequalities. But here we are interested in term sparsity, which I highlight here in this example of what's the motivation behind. So if you take this polynomial, for example, and you want to represent it in this basis, so here I just flipped this one and this one, but then you have, you write it this way, but here you can see that here there is many zeros. So this vector is many sparse, which means actually that you don't need all the components of this basis to represent this polynomial. And of course, this is just an unconstrained example, but with constraint it's a bit more complicated. The idea behind this is what you do is, since that the moments matrices, they are indexed by the basis because we have this tensorial product and in it. So there is 2 ideas. The first is to use reduced monomial basis, so to select one of another smaller basis than this, and to use it well in the moment sum of square, and which will give smaller moments matrices and a better complexity. But the problem is what basis usually? It's not always there. Like there is no general procedure you follow to find such a basis. So it's really problem specific. But I will come back this later in the context of frame structures. And there is a second thing we can do is the term sparsity pattern technique. And this one is a bit generic and can work, like one can apply it to any kind of problems. And the main idea of this term sparsity technique is to find some subsets of this basis. It can be partition or no, it's not important. But the aim is to replace this by, to use these smaller subsets and to decompose the matrices according to these subsets. And therefore you will have smaller but many matrices like this instead of these conditions. And this usually it improves a lot the complexity, especially when these matrices are small. And now the term sparsity technique, just to highlight it very quickly, is through an example. So you take this, for example, this problem. What you do is you compute the support. So the support, you just take the monomials that are present in the problem, and you build a graph where the nodes are the monomials and the link between them if the product is included in this support. And what you do is you add some other monomials that are not present, but what you're going to do is algebraic closure of this set so that it will be small, but it still give feasibility. And then you compute a chordal decomposition, a chordal extension of this graph. And why? Because it will allow you to decompose it into cliques, and actually it's these cliques that you will use to decompose your moments matrices. And of course, you repeat this. You can repeat this operation until you cannot repeat it. And every step is, we call it a sparse order. And for the frame structures problems, actually, we remarked that this problem have a special structure. It means that it's separable in the sense that there is no mixed monomials appearing in the problems. So here we propose to use this basis, which we call non-mixed term basis, which actually we just take the standard basis and we eliminate all the mixed terms in it. So here a first numerical example. So we take this problem, and here there is this optimal design. And here we compare different instances of the moment sum of squares. So here there is the dance, and then there is the DSP technique with k equal to 2, then there is where we use the non-mixed term basis, but with the dance, and here it's a combination with DSP and NMT. And this K represents the sparsity order until which we've gone for the. So here you can see the results. Here is the optimal values, here the number of variables, and here is the time in seconds. So you can see that here, while using this NMT basis, it reduced drastically the computational time while keeping the same global. Actually, here in bold, it means that the global optimal were certified. A second example, this one is a weight minimization. And here we can see that for relaxation 3, only the dense moment sum of square was able to certify the global optimality, while the others reduced the time, but they didn't reach it. But what is interesting here is when we increased the relaxation order, then we were able to, with both sparsity methods, we were able to reach the global optimality. And you can see that here the time is still much better than to use the dense moment sum of square hierarchies. And the last example is this one with a lot of variables. So with the dense moment sum of squares hierarchy, we were not able to compute the solution. But you can see here that with the reduced basis, we were able to certify it, even with a lot. It takes some time, but we were at least able to certify global optimality and to reach it. And for NMT, we were almost certifying it, but the time is drastically really smaller compared to the others. So it's at least it's a very good lower bound. So just to conclude what we did in this work, so first we adapted the existing DSP techniques to address polynomial matrix inequalities, because in literature it was only for the scalar inequalities, and this will allow to the applicability to a broader class of problems. And then we introduced the use of non-mixed term basis in the context of frame structures, but this also can work in any other problems that have this separable nature. And of course, we demonstrated its convergence with many extensive numerical experiments. And we showed that these techniques, either if it uses it separately or in combination, it improves scalability in global in polynomial optimization. And in the worst case, which is typically when you use this DSP for very small sparsity order, then sometimes you don't reach the global optimum, but you still have a very high quality lower bound with very, very small amount of time. And thank you very much for your attention.
All right, okay, thank you very much. Yeah, it was good timing. Thanks a lot. And now I give the floor to our the committee to ask questions. If you please can ask in English, it'd be better for him. So if there's, please go
I
ahead.
have one question.
Mm-hmm.
I understand that all is about this term density technique, but I have a specific question concerning page 12, where you talk about this Hordle extension of a graph.
Yeah.
I wonder whether you have which algorithms or software you have used for this purpose. I mean, computing this Hordle extension, whether you use some algorithm which were in graph theory available, or you code it yourself.
No, we use actually we have some. I think no, it's yeah. We use some algorithm, and usually it's this maximum. Minimum filling, or yeah, it's this classical algorithms for extraction of this Cordel to make this Cordel function. And yes, I think it's Marek who coded them in, like, when we have this big repository of the codes. Yeah, we have some kind of codes to do them, like, yeah, and it's available. Like as I show in the end, everything is available here.
Thank you.
Mm-hmm. Any other question? Okay. Maybe I will ask one, just a general one, because my understanding is that you are you have extended the technique to be applicable to a broader class of problems, as you say here.
Yeah.
And you also show that in your experiments that it's faster. And I'm not an expert in this field, but so there aren't really any competing other methods that can be used. Or have you tried any other approaches? Or it's
yes, there is other methods, which is this, for example, this correlative sparsity.
Mm-hmm.
Here. There is a correlative sparsity, but for us it was not evident to use it because the problem is we have. Actually, the correlative sparsity doesn't act on monomials but on variables. And the problem when you have a pole constraint, for example, you cannot apply the correlative sparsity because your correlative sparsity needs to decompose the problem into subsets of variables. So when you have one constraint that link all the variables, then this becomes irrelevant, or at least you have to try to come up with something else. And another work which was submitted this year is regarding the structural sparsity. Actually, when you have this big matrix from from here, yeah. What you do is you apply some decomposition on the matrix, and then you include it somehow into the modes somewhere. But then this method actually it works also as a complementary of this term sparsity. Like it works very well while coming. But yeah, there is also many other methods, but sometimes it's kind of problem specific because some methods are not applicable at some kind of problem. For us, it's really good to have term sparsity because our problems, for example, doesn't include this kind of mixed monodom, so it's really term sparse. Like there is a lot of sparsity in it, like in this.
Right. Yeah. Thank you. Thank you.
I'm not sure if I understand your technique well. I'd like to ask. So you have some optimization problem, and you solve it. You add some sparsity assumption and show that your result or optimized value will be the same as this dense problem. So it is. I wonder if my feeling is correct, and if you can somehow characterize, because not for every task it is possible that you incorporate sparsity constraint and you receive the same solution. So it is only some class of problems that has this property that you can incorporate this.
Yeah, actually, the whether you can apply term sparsity or not, it's in the nature of how the polynomials that defining the problem are. So usually, the term sparsity is something you can almost all the time apply, unless you have all the polynomials that are written in the full basis, they require every monomial in this basis, but usually you always have some, like when you write your polynomials either in constraint or in the objection, you always don't use, like often you don't use all the monomials, like it's, and usually when you have this, then you can apply term sparsity, or yes, you can go, like this is how you recognize whether you have this term sparsity in your problem or no.
Right. Well, if there aren't any further questions, then Marwan, thank you for your presentation and for answering the questions. And now I will ask the other contestant, who is Marko Ruman, who is also online, to share his screen with us. I've noticed that.
Okay.
Yeah, just wait a second. I try to make it bigger.
Okay.
You know, maybe. Okay, let me start the timer for
So
you.
is it possible to switch on also this place? Because
No, there is. It's.
visible.
We wanted to put it on the other screen also. Can be done, I think. Maybe you can do it, yeah. You can do it. That's faster. All right, let me. So Marko, you can start.
Okay, so good morning everybody. Let me present my work on knowledge transfer in deep reinforcement learning, and more specifically it will be about a method we proposed about learning of a correspondence function between two tasks. And this is a work that I've been working on with my supervisor, Dr. Guy from the Department of Adaptive Systems. Let me begin with a bit of a background. What is a reinforcement learning task? We usually model the task as a Markov decision process, which most of you are probably aware of. The environment is at some state, so we have a state space, and the agent is interacting with the environment through some actions from an action space. Then the Markov decision process has a transition function, which ties how the states evolve over time, and a reward function that rewards the agent for the desirable strategy. And the goal of the agent is to maximize the accumulated reward function and learn a strategy that does that. In the reinforcement learning tasks, the key constraints are that the transition dynamic function or the transition function and the reward function are unknown to the agent, and he learns it progressively with interactions. Our specific problem formulation, so we're talking about knowledge transfer. In our specific scenario, the agent has already solved one task, which we refer to as a source task, and he's now faced with a new task called target task, which is yet unsolved. The agent solved the first task and he generated some knowledge. He generated a set MS, which are observations collected by the optimal policy. Then he learned the optimal Q function, which is a function that tells him which action to take at which time step. And he learned also an environment model, which models the transition function. It tells him which the next state will be. And then he interacted with the target task by using a random decision rule, and he collected some observations from that task as well. Now, the crucial assumption for this setting is that we have no paired data. So both of the data sets, MS and MT, are collected independently. And the objective of our agent is to learn a correspondence mapping that takes a state from the target task and maps it to the source task where the agent knows what to do. He has the optimal Q function. So this way, we want to use this strategy to solve the new target task. And why this problem is crucial, I will give you like two examples to motivate it. First one is so-called simulation to real transfer. The reinforcement learning methods are very capable. Just they require a lot of time, and if we are training physical robots, also a lot of it costs a lot of energy, a lot of material, etc. So if you imagine training an independently flying drone over some danger area, it would take a lot of time to train the drone in real life. Instead, what we can do is to create a simulator, train the algorithm there, which is much cheaper, and then use a knowledge transfer method such as the one we propose, and transfer the knowledge to the real world, and we can solve this problem this way. Another motivational example is like much higher generalization and way of learning for the agents, because most of the people know how to drive a car, then learning how to drive a motorcycle becomes much easier job than learning the motorcycle from scratch. In reinforcement learning, this is often not the case, and it's more optimal to start from scratch, which our method can help with. So let me move on to the core contribution of the paper. Usually standard methods such as CycleGAN for mapping to unpaired sets, they usually measure similarity only in so-called visual space. So they take individual images or individual states in our case and try to find mapping between those. But the idea for reinforcement learning is that it's a much more complex scenario. We don't have just individual states, but we have also the dynamics, we have the strategy, the optimal strategy that the agent uses. So we came up with something called, or let's say like threefold proximity metric. It's a way how we measure the similarity of two reinforcement learning tasks. And we argue that if we are learning the mapping, the correspondence function mapping, we want it to be useful, valid for mapping to reinforcement learning tasks. We need this more complex proximity metric, and it consists of three types of proximity. First is perceptual proximity or the visual proximity. It's what the usual models work with. Do the states look consistent? And then we added to that so-called strategic proximity, and we don't care about the individual states only, but we care also about their decision value, which is measured by the Q function. So something that tells us which actions to take at each individual time steps, and also dynamic proximity. It means, do the transition obey the same physics, like if we transfer them among tasks. As I said, we took inspiration from CycleGAN framework for mapping to unpaired memories. And the CycleGAN learns basically two mappings, from one set to the other one, and from the other one to the first one. In our case, it's two mappings between two tasks. And it already has, in its laws that, CycleGAN laws that we train the mappings on, it already has this perceptual consistency in its loss. Namely, it has two parts of loss that we train. First one is adversarial loss. It's a loss that forces the mappings to match the distributions between the sets. And then we have cycle consistency loss, which forces the mapping to be bijective. So when we map a state from the source task to the target task and then back, it should be an identity mapping. And this has been already included in the CycleGAN. We extended this loss to make it much more suitable for reinforcement learning. We added two components. First one is a Q loss, which embodies the strategic proximity. So it's a similar approach. We are trying to force the mapping to be bijective, not for individual states only, but we want it to retain the Q value of the state. So when we map a state there and back, we want it to have the same Q function, so Q value, which is crucial for choosing the strategy. And then we added a model loss, which embodies the dynamic proximity, which means when we encounter a transition from a state ST to ST+1 in the target task, and map both of the states to the source task, we want it to be like a real tangible transition that is observed in the source task. That way we preserve the dynamic dynamic property of the tasks, and it makes it even more suitable for reinforcement learning if we learn a mapping like that. And so what we got is a generalization of generative frameworks. We optimize this weighted sum of 4 loss components. And we can see that if we set those hyperparameters, those weights to 0, if we set all of them to 0, we're getting the standard GAN framework. If we set just the newly introduced one to 0, we get the standard cycle GAN framework. And if they are non-zero, then we have our extension suitable for reinforcement learning tasks. We tested this approach, this method on a relatively simple example. The agent already solved a source task, which was a Atari Pong game. It's a game where the agent plays against the computer. The agent solved this using a standard DQN method. And then he was faced with a new task, which was the same as the source task, just the observations were rotated. And we tested 2 different architectures how to construct the correspondence function. Just for simplicity, we chose to use rotation generator, where we optimized just the rotation parameter. And then we had more general deep neural network followed by a rotational layer. We have some key findings connected to this experiment. First one is that the fine-tuning fails. What I mean by that is we tried to just reuse the Q function we learned on the first task, and because the tasks are the same, just the observations are rotated, we wanted the agents to play it and fine-tune it while interacting with the environment. However, it turned out to be less effective than learning it from scratch. The red line is the fine-tuning method, standardly used in transfer learning situations, and blue line is learning from scratch. Then, when we used the simpler rotation generator, we achieved what I call 100% knowledge transfer. So right from the beginning, the agent learned the rotation, and it's important to say he learned it in unsupervised way, so he didn't have the pairs of observations, he just observed one set and the other, and used our method, and he was able to play the game right from the beginning. For the more complex one, we achieved a partial knowledge transfer, is the orange line. The orange line showed better performance than the blue line, learning from scratch, but not as good as the rotational layer. One downside of these generative methods are that they are not easy to make them converge all the time, but we still achieved a good, significant knowledge transfer. So, just to conclude, our contribution lies in, let's say, defining in an indirect way a proximity metric for 2 reinforcement learning tasks. It is based on visual, strategic, and dynamic alignment of the tasks. We used that proximity metric to train and create a practical method for learning a correspondence function between 2 tasks, which is a generalization of cycle GAN framework. And we demonstrated that this method has potential to work for two different reinforcement learning tasks. And it worked in situations where standardly used fine-tuning or just using the cycle GAN failed. So that is briefly it, and thank you for your attention.
Right, thank you. Thank you, Marko, for your presentation. And now again, it's time to ask questions. I ask the committee, please.
Again, I will start. So, as I understand, so your contribution is mainly about this reinforcement learning. And in one of your, I have a specific question concerning one of your first pages, where you have written that you got inspiration from the so-called cycle GAN techniques. And And I wonder how old is the technique, who developed that, or whether you could, so how old is this, who brought this technique?
Like a cycle gun, I believe it was introduced in like 2016 or 2014, something like that. I don't know if it answers your question. I believe so.
Yeah.
But I'm not sure about the specific year. It's relatively recent, but not in the last 5 years.
I more meant who developed the people, I guess. Whether it was here in Utea or outside.
Yes, who developed it? Well, I'm not sure if I know the name right now. I think those were researchers from one of the, I think it was Yale University, but I'm not really sure. But it's a framework that is commonly used for images mainly. Those maybe you've seen. Like a couple of years ago, it was very popular to find mapping between, let's say, photos of landscapes and paintings of some famous painters. So the model was able to transform your photo of a landscape to a painting done by Monet, let's say. So it looked very similar, or it applied its style to your photo, something like that. This is why it became kind of known back then.
Mm-hmm.
I'd like to ask, you showed performance of your technique on some computer game, if I understand. Could you give us more details about this computer game? What are the rules, or what is objective of this computer game, or what's going on here?
Yes, sure. Like the game is relatively simple. It's called Pong, so it's basically like a very simple version of a ping pong game. I don't know if can you see my cursor?
Yes, yes, we can. Yeah.
Okay, so like this paddle on the left is controlled by a computer. You don't have any influence on that. Mm-hmm. And this green paddle is controlled by you or by the agent. And you're moving in a vertical dimension, and there is a ball. And the ball is traveling from one side to the other, and your point is to protect your space, so you have to bounce the ball back, and ideally the ball should end up in the left side of the screen. That's how you get a point, and here you have the score of the game. And I think like the total set of points is 21, and who has more points at the end wins. So it's like a simple tennis, let's say, kind of game, or ping pong.
So you mentioned something about the convergence, right? That the convergence is not always the best of the algorithm, which is, I mean, this is something common for the reinforcement learning algorithms. But do you have some theoretical knowledge, especially about variation? Because in the paper you also here you always present the averages, right? The average reward, but how precise that is, right?
Yes, like. That's a very good question. Also, what I maybe didn't mention, to find this correspondence function is computationally not that cheap. So it takes a lot of time. And for the article, it would definitely deserve a better analysis of convergence, etc. Just at the time, I didn't have enough time and resources to make the analysis correctly. So we got some results, but the practical results are more like illustration of the method rather than being like an experimental evaluation of it.
And from your practical results, do you have some notion about the stability of the algorithm? At least,
The important notion I have is because when we apply, when I go to this slide, when we apply just the standard cycle gun, so we put those added elements to 0, we can sometimes achieve some results. We can be lucky and it works, but by adding those two elements, we make the method much more stable. so it converges more time. But I cannot give you a real like a estimate how much more stable. But I can tell you that it helps, definitely, significantly it helps.
Okay, perfect. Thank you.
Yeah, maybe I have a follow-up question that Jože was just asking, because I know cycle guns are extremely tricky when you try to train them, and especially the gun in general is very tricky, that you have to switch between the minimization of the generator and the discriminator, and that. So this could be, I guess, the problem here, that the stability is not guaranteed, but there's really no, I'd say, like a theoretical way how to determine whether the cycle gun will converge or not. But my question is now, I guess there must be some kind of a limitation, maybe, what kind of knowledge transfer functions you can learn. I mean, it could be possible that when you have your target and your source problem, that there might not be any transfer knowledge function. It might not exist, basically, because these two tasks are not comparable. Have you thought about it? I mean,
yes, like we commented in the paper, basically we assume that the tasks are similar, and by similar we mean that there exists a mapping, such a correspondence mapping that helps at least partially. So in like proper terms, we assume that the two tasks have a correspondence mapping. When used, the agent performs better than a random decision rule. So this is the assumption made for our analysis. But definitely you're right, like if we take two tasks that have nothing in common, we cannot find any correspondence function, definitely. But yeah, it has to be used with a bit of caution, for sure. We cannot use it just on two random tasks and hope for the best. It's not going to work.
Okay. Wait, just one more quick question. And this knowledge transfer using cycle guns for that, this was your idea, or it has been proposed before?
I've seen a paper a long time ago that used the cycle gun, and it worked like for a very simple example. Like they used it on a slightly different game, but they did something like they added some artificial obstacles that confused the agent, and by using cycle gun they were able to remove it. But when the tasks were a bit more different than that, just the rotation, it didn't really work well, or it didn't work at all. So then we needed to add some more specific loss components like we did, and it improved significantly.
Okay. All right, thank you. No, I like the idea. I know it seems to be really clever, and I like it very much. So, okay, fine. So if there are any further questions, then we will proceed. Thank you again, Marko, for giving us the presentation. And now we will switch to my laptop. And let's switch the screen. And yeah, so now I will ask Antonia, Soncha, please. I've changed a little bit the order, I'm sorry, but it was because I want those who are online to be first. Maybe můžeme tohle taky přepnout tam, ať je to jako je tam nepotřebujeme už. Myslím, jako co?
By to tam bylo u sebe. Takže ona jen zasunula ta obrazovka, by to odpadlo. Tady to teda.
Já tak můžu třeba ukážu. Já jsem se díval pro ten nápět.
No takhle.
To byl můj plán, ale
Já jsem to špatně pochopil.
jo.
Tak já to mám to zase poté.
To je levý nebo pravý?
Levej.
Tak až to dojedeš, jo?
Teď můžete dojet.
A jo.
A to.
So Toncha, I ask you, you have 15 minutes, I will just start. Okay, the floor is yours.
So good morning, everyone. Today I will talk about our paper that's called Spatial Temporal Source Term Estimation using the Deep Neural Network Prior and its application to Chernobyl wildfires. So firstly, to explain the problem we are trying to solve. In this case, in April 2020, there were wildfires in the Chernobyl area, and because the soil and trees are contaminated, cesium was emitted into the air and it was transported around Europe. And there's a whole network of measuring stations that detected higher concentrations of cesium. And then they could ask what was the total emission of cesium, how much it was emitted into the air, and when exactly it happened. And also we can ask where exactly it happened, because since the wildfires were on for a whole month, they actually changed their location. Starting here, it was spreading in this direction, and also it started here. And then in the second part of April, there were new outbreaks in this area. So the source term is actually spatial as well. So to give it some mathematical model, this problem is called atmospheric inversion. Basically, we have some measurements of the concentrations or deposition of the cesium. And then we have the source term that we want to estimate. So that's how much cesium was emitted at a given time and location. Their relationship is assumed to be linear, where it's described by source receptor sensitivity matrix. In this case, we denote it as M. This matrix is typically known. It's pre-computed from some atmospheric transport model. So we are assuming now that this matrix is correct, and we only want to estimate x from this linear equation. So this problem is imposed. The matrix M is quite large, it's ill-conditioned, and also typically we want to estimate a much larger source term than we actually have observations. So there's a lot of local optima, and we need to regularize it or add some prior information. Typically, in atmospheric inversion, prior guess is used. That means that they have some prior information about from some other data, for example, how the emission actually looked like, and they are trying to fit the new data so that it also somehow works with their prior guess. While this works very well, the prior guess may be biased, and also it's not always available, so we need to use something else. So when there's no prior guess, we can use some Tichonoff regularization or some smoothness prior, which typically leads to Bayesian formulation. So we decided to take a look at it from some more novel perspective and use deep image prior. So deep image prior was proposed for image reconstruction. So you may now ask how the source term is an image. Well, in this case, we are assuming that the source term is spatial. So we can actually take a map of concentrations of the source term, grid it, and then each element can be considered a pixel of an image. Also, it has some time evolution, so you could understand it as a video. And both in the spatial domain and also in the time axis, we can probably expect that it's kind of smooth, that it doesn't change too quickly when we move from one pixel to the neighboring one, from one time step to the following one. So we can understand it as an image and use deep image prior. So what exactly is deep image prior and how it helps? Well, the idea is that the structure of a neural network itself is a prior for the problem. In the case of the images, usually it's convolutional networks like UNet. And we already know that these convolutional networks are biased towards images that are smoother and natural looking. Here I have an illustration of a very small and simple UNet. It actually has two layers. There's a top layer and a bottom layer. Each layer has only one channel, so there are only two convolutional kernels that are trained during optimization, and there's also only linear activation. On the input of our UNet is noise, let's say. In the deep image prior approach, the input is usually noise. And here we have one pixel that has a high signal, so that we can illustrate how the convolutions propagate through the network. So we can see that on the top layer, or on the top level, the convolutional kernels create like short-term dependency, because the output here is just the closest neighboring pixels. But thanks to the downsampling and later upsampling from the bottom layer, we can see that it creates longer dependencies. So this one pixel, it was only one pixel at the beginning, the convolutional kernel on the bottom layer spreads over a larger area. So this creates longer dependencies than just the neighboring pixels. We can also take a look at it from a point of linear operator. If we have this simple UNet, we can actually understand it as a linear operator, and then for a normally distributed input, we actually know how the covariance matrix looks like. And here is an image what it looks like for this very, very simple UNet. And we can see that it actually creates block diagonal matrix. It's quite easy to understand. So how do we use it? We use a Bayesian model. We assume that the errors are IID distributed according to normal distribution, so the likelihood is normal. We actually have a prior for the source term that is formulated as a ratio between two neighboring fractions, but we only enforce it numerically. And then we choose the posterior to be normal distribution as well, where the posterior mean and posterior variance are obtained by the deep image prior. This means that we have one sample of a noise that's inputted into the UNet, and there are two outputs of the UNet. One of the outputs is the posterior mean, and the second output is the posterior variance. And then, because we have a Bayesian model, we minimize feedback-Leibler divergence between the real and approximated posterior. And during this minimization, we train the parameters of the network, and this way we obtain the posterior distribution. What is also special about our approach is that the source term is actually 5-dimensional. It's not only spatial, it means longitude and latitude and in time axis, but we also consider height above ground level and size of particles. We do this by using 3D convolutions for the spatial and time axis, and the other two dimensions are treated as channels and backsamples. So for the final algorithm, there are two more steps that I haven't mentioned. Firstly, we pre-train the neural network because we have random initialization of the neural network, and this introduces too much stochasticity. So we pre-train it to output constant array before we start the inversion. And then we also run it 15 times because then it's still too random, and we get a lot of let's say a lot of local minima. And after that, we just take average of the posterior means to find our final estimate of the source term. Now, to the results and what it actually does for the Chernobyl wildfires, we compare the method with Tikhonov regularization, which is a simple method, so we want to ideally outperform it. And we compare it also with a prior guess formed by Kovalets and his group that was obtained from satellite data. So this estimate or this prior guess is not found from the data we are using. So firstly, we need to check if our model actually predicts the data well. And we can see that our method UNet posterior fits the data nicely, but still it's very similar to Tikhonov. Tikhonov is successful from this point of view as well. So it's not only about the fit to the data, we also want to see how the predictions actually look and if they made sense based on what was already discovered about the source term, how it should look like. So we can start by looking at the total emission. The red color here shows Kovalets' first guess, and we can see that there's a pattern in the emissions through the month that is followed by both UNet posterior and Tikhonov. So from this point of view, our method works quite nicely, following the correct peaks on 5th, 9th, and 16th April. But there's a problem with the days where there's no emission assumed by Kovalets, especially here on 14th and 15th April. And I think our method can't really estimate non-zero emission here because we assume the smoothness in time axis, and that means that we can do really this sharp difference in the total emission. Now to the spatial estimate, which is the most important thing that this method brings. We can again compare the spatial pattern with the Kovalets' first guess, and we can see that the highest emissions appear in the same areas in our prediction as in the Kovalets' first guess. Compared with the results obtained with Tikhonov regularization, our results are much more smooth and compact, because Tikhonov has a lot of artifacts in the estimates which does not appear in UNet posterior. On the other hand, we can see that there are some artifacts in our method as well, and it's usually the areas where there are artifacts in Tikhonov regularization as well. So our method, thanks to the averaging of 15 runs, also offers a way to quantify uncertainty of our estimates. Here we can take a look, for example, at the 17th April. This part of the estimate is not in Kovalets' first guess. And when we plot this way the total emissions from the 15 runs, we can see that for this pixel, there's a lot of differences between the 15 runs. So there's higher uncertainty compared to this area where we agree with Kovalets' first guess. So to conclude, we proposed a new method for atmospheric inversion that uses deep image prior, which is a novel approach because neural networks aren't typically used in this area. We accommodate 5D source term, and we does not require prior guess to actually find a solution that is meaningful, smooth, and compact.
Perfect. Thank you. Thank you. And now it's time for questions again. So please.
So my understanding is your paper is mainly about Bayesian modeling, but you use some methods of this neural networks.
Yes.
So it's a continuation of your method. So one of your competing methods you made was a Tikhonov method. So I wonder what is the method came from method in Bayesian approach, or is it comes from neural networks where with competence come?
Well, so the Tikhonov approach is, I would say, a very old method. It's a very old regularization. From Bayesian point of view, we can say that it's a prior where there's a normal distribution with zero mean. So basically, in this case, it would mean that the prior guess is zero, that there is no emission at all. But Tikhonov regularization, I think, is very typically used in all inverse problems, basically forcing the unknown parameters to be as sparse as possible.
So it comes from Bayesian modeling, yes?
Yes,
Yeah, okay.
I would say that.
I'd like to ask,
Yeah.
you compared it with the covalence pulses. Is it kind of measured data after some measurements has been gained, then it is compared with your prediction, or what is it?
What is it? It's actually taken from a supplementary from his paper about inversion. It should be created from satellite data of the fires, and he also combined it with some information about how the area is contaminated by the radionuclides. So somehow he combined these informations to create this prior guess. But it's still only a prior guess for him. He then uses it together with this data set to find a better solution. But we don't really have this spatial estimate from him, so that's the reason why we compare it with the prior guess.
Let me ask one question, maybe the last one. You are using this deep image prior, but the variational version.
Yes.
I didn't get it, and I also, after reading the paper, I went very quickly through your paper, so I just probably miss it. It's not clear to me what is do you use the variance that you also estimate with your network? Because you use,
No.
you are not.
We don't use it.
So why using the variational deep image prior and not using the standard deep image prior?
Well, if we use the standard one, probably, yeah. Well, I think that the variance actually helps to kind of stabilize the estimation, to force it towards the Gaussian posterior. But then, as a result, it would be very nice if we could use the posterior variance, but unfortunately it's estimated very low and it doesn't really give a lot of information. So.
Okay. So, if there aren't any further questions, then thank you again, and let's move on. And the next contestant should be, yeah. So, let me switch to your presentation. Oops. Spoiler, I'm spoiling you. Okay, let me start the timer again. So, stage is yours.
Okay, hello, I'm Jaroslav Knotek, and I'm a PhD student here, but I'm also affiliated with Center of Research in Třešť, or it's called, we have a Ústav jaderného výzkumu. It's a research center that focuses on research of nuclear materials and inspection of nuclear power plants and stuff like these. So right off the bat, the problem in our domain is to actually share our findings. The whole field is limited by some security measures that prohibits us to actually share our findings, to properly calculate or evaluate our methods because we don't have enough data, and so on. So in this paper, I focused on taking a step back, and instead of focusing on actually coming up with some calculations or new methods, I tried to enrich our data sets or our way to actually collect relevant data. I'll be talking about the inspection themselves. What are we talking about when we mention inspection data? Then we will talk about how the defects or anomalies or anything we would like to find in the data are imitating at the moment. We will talk about some motivation, how the simulations and synthetic data can actually ground ourselves in the research of others. And then we will get into the actual simulation. And also, the problem that I'm trying to solve is also a problem of this presentation, is that I can't share any real data with you. The inspection of nuclear fuel is strictly prohibited to share among even the community. For each individual image, I would need to get a separate confirmation that I can share it. So this is another problem in this field that I'm trying to tackle. So this whole initiative starts with power plant, or yes, nuclear power plant. We have, for example, Temelín in here. It's a power plant in Czech Republic. There is 2 blocks down here, and what we can see inside is a reactor hall. It's a huge room with enormous pool that contains a reactor. Reactor itself contains these nuclear fuel assemblies. It's actually a bundle of rods that contain the actual fuel. And this is what we will be modeling in this paper. We are trying to model this object, and we are trying to inject some defects that the methods that we are developing are trying to find. The inspection itself is actually putting these cameras on the camera ring into the pool and then pulling the fuel assembly through it. So it takes a video from each side of the fuel, and this is our data. This is where all our other data processing pipelines are starting from. So this is a starting point, and each camera is presenting or is recording a frame that looks like this. What we can see here is actually the bundle of rods, and they are stabilized together with the object in the middle. It's a spacer grid. The inspections are focusing on several things. One of them is the physical integrity of the bundle, of the assembly. If there is something wrong, for example, rods are touching or there is some foreign object, it may possess a risk, and this fuel needs to be taken out and replaced with something else. So we are focusing on whether the spacer grid has all the aspects it should have to make the next round safe. Also, their foreign objects could possess a huge security risk, and it needs to be taken out. And there is a risk for older fuels when it runs for some time. There is some material tension that can result in 2 rods actually getting closer together, and that it may compromise the material itself, so they actually think that this is a very risky situation, so it's also a reason why we should pull the fuel out and replace it with something new. And during the inspections, we are not only trying to find problematic areas, but we are trying also to evaluate the state of the nuclear fuel assembly. So we are focusing on how it's bent, what are the visual properties of the surface of the rods. We are trying to estimate the growth of the material, the metals and things like these. So there is plenty more that we try to do with that. In order to develop any algorithm, we need to have a data, and the data should have the data and measurements. So far, we started with just the inspection videos, and we were supposed to measure how the shape of the fuel changes. The problem is that we didn't have any real data, any real measurements, because it's not possible to go into the go into the pool or to see the fuel ever again. So what our colleagues from China did is they used a clean one. This is a blank fuel assembly, and they used jack and they actually physically bent the fuel. This is something that we can't afford, so we couldn't have this data. So we decided to go with the simulation thing. But a few years ago, what we did is we tried to focus on the surface, but the problem is once again that we can't really get into the reactor and stage some problems there. So we had to create our own experimental environment. So we did things like these. You use paper whitener, you apply it on the surface, and you use some acid, and you try to imitate the real oxides in this manner. But also this is very limited approach. So we were trying to look around to see whether it makes sense to avoid the physical simulations and try instead some kind of a virtual one. There is one paper which focuses on automotive. What they did, they tried to train instant segmentation on the data from games, and they actually improved their performance. If you are interested more, then I would recommend to read a Playing for Data Ground Through from Computer Games paper, which will describe this in more detail. The same applies to Microsoft paper. They developed 3D renderer. They try to imitate all the possible variation of the population. So they rendered several millions of pictures, and they trained a landmark estimator that focuses on brows, noses, lips, and things like this. And they actually improved. They trained it purely on the simulated pictures, and they improved the accuracy of the state-of-the-art model. So now I'm going to talk about the simulation itself. It's actually very, very trivial. We are using a 3D renderer that has a Python interface, so we can script everything in there. We can create some templates and play with parameters. We chose Mitsuba because it's photorealistic, and it also allows some simulation of photons. If we want to focus on the material and all its properties, we could. The main thing of this simulation is to create a 3D model. The model isn't created in any editor. It's scripted, and it should offer us the way how to manipulate it in order to create some anomalies. If there was some kind of designer who created by hand, it would possess the same limitations as manual experiments. So we created a script that generates different types of spacer grids, which is a model like this. We can model it from a one teeth or one simple part that's actually repeated and copied over, or we can create it as a whole. And we have another objects, rods and caps, which is a thing that is on the top of the rod, and then we can create a model. The last thing that remains is to actually add a material, which is problematic. We know exact the composition of the material. The problem is that in the time the material gets oxidized. That impacts all the visual properties. And we need to simulate this. So we used some properties of the renderer. We used inverse rendering to estimate the impact of the oxidation. And as I talked about, we needed a way how to manipulate with the model, so that it can give us some kind of anomalous data that we would use in evaluation. And this is what we do here. We generate some bending and bending of the whole object, and we can bend individual rods themselves. So in the end, we have ground truth, and we also have the data, which is the same thing that the Chinese people did with Jack, but we can do it for any number of fuels that we would want. And in the end, this allowed us, for one, it allowed me to have this presentation, because otherwise I wouldn't be able to talk about any visual data that we have. It also allowed us to evaluate the precision of the algorithms that we already have, that focuses on all the aspects I talked about. And it also allows us to create data sets for students to start with and to enrich the data sets that we have with some behavior that is not usually present. For example, when you have the oxidized fuel, there is a very problematic situation when you have these white spots. This is very problematic, and it's also almost never present in the real data. So we needed to create it ourselves, possibly without a paper writer. So these data are created synthetically, and then they are blended into our data sets that are focusing on those anomalies. And since this is just this paper focuses on building a ground for some future improvements, so I will give you just a taste where we would like to focus, and we would like to get more into the estimation of parameters of the lighting conditions, the way that light behaves in the reactor, because there is some environmental changes that are not straightforward to understand, and also to extract the specific changes of the material, visual changes, so we could enhance the models that we have. And the next thing is we need to focus on the simulation of oxide layers, because it's a very important indicator of some other behaviors that I will not get into it now. So this is something that we will be focusing on next. Those are actually the interesting things, but it wouldn't be possible without building this simulator now. So that's it. I think that yes, this was the last slide. And if you have any question.
Yes, so committee, go ahead and ask questions.
What I a little bit missed in your presentation is a description of the methods. I understand it was nicely to follow, but what I did not get from it, whether you propose some algorithm or use some software which was available and combine that, or what was somehow behind, yes?
So we have a general 3D renderer, and everything else we scripted ourselves. So all the behavior changes, all the parameterization, all the extraction of materials or injection of them. Everything else was scripted. So
you did it very well, but you have not described it too much in the paper. Is it?
yeah, well, it's described in the paper, but the process itself is straightforward. It could be most of the content of the paper, of the methodology, is very trivial. We just come up with some models, we vary it a bit, and then we extract it in the form of a video. This is straightforward. But what this paper is focusing on is more of the impact, because the nuclear engineering is a very old field that really resists any changes. So what you had 20 years ago with the medical domain, when they opened up, they tried to think about how to present the data to the scientific society so they can develop any algorithms. Nuclear energetics hasn't done yet. And they are trying these approaches for bending physically the fuel assembly to get some data. And so that's why I'm not talking much about the method, because it's basic 3D rendering. I'm talking about the impact that this paper should have.
I do not understand, because in some cases you don't have ground truth. So you are just extrapolating that you mount something and it should work in other cases.
Yes, we have developed methods that lacked those ground truth, but now we created some data that have the ground truth, and we used it to evaluate our methods we developed before. So yes, in the end, now we have the data, and now we have the precise insight into how the methods work now, but we didn't have it when we developed it. That was one of the motivation why we decided to create this simulator.
Just small question. You focus on images only, but the detection of fault is done also through the noise records and data of this type. This is very much used. Do you plan to simulate also sounds type thing?
No, well, no, because we are focusing on non-destructive, non-destructive simulation.
These noise type things are used also for non-destructive things.
Right, you mean
essentially there are sensors on the reactors recording noise produced by this and extrapolated to recognize whether there is some fault there or not.
Oh, I thought you mean the ultrasound songs. No, we are not planning to do this, but we are planning to simulate the effects of water and its temperature, because the temperature as it rises, the water itself behaves differently on every reactor. That's the reason why after the inspection, when you pull the fuel out, you don't put it back where it was, but you shuffle it around in order to prevent some things that stems from this, and we are trying to incorporate this behavior into the simulator. But no sounds yet.
Okay.
All right.
Maybe a comment. When you submitted an patent application of this topic or not?
Yes, we have several, because we have plenty of algorithms that sorry,
go ahead.
They do something interesting. We are stitching the frames of the video. We are trying to detect anomalies on it. We are composing. We are validating the fuel integrity. We are trying to find correlation between this and some other things, but none of it is possible to present in full. The computer vision algorithms we have developed are the huge problem itself, because it really, usually in order to create a serious paper, you need to have a data set, you need to have all the experiments, but since we can't really present our data, we really struggle with coming up with something else. So yes, we have patents open at the moment. I think that it was for the stitching itself.
No.
So we use the video in order to stitch it into one large image that is much easier to navigate and consume by our other pipelines.
Okay. Thank you, Ara, for this presentation. And now the next contestant is Václav Kušník. Václav, come here. And Oh, you have a telephone. Okay, started.
So I will be presenting an article published in Pattern Recognition Journal. It was accepted in August this year, and it deals with the problem how to handle blurred images in image recognition. Currently, I would divide the main approaches to this problem to three categories. So first, we might try to reconstruct the sharp image by the convolution, which is in general a difficult and ambiguous procedure. In deep learning methods, blurred images are usually handled by data augmentation, which means that we artificially blur images from the dataset by various blur types and intensities during training. And finally, we may design handcrafted features that are invariant to blur, which is the approach that our paper is focused on. This theory first appeared in the 90s, and since then a lot of papers were written about it. And this paper I'm presenting, this article, generalizes the theory to color images. We normally model blur as a convolution, which is a compromise between reality and mathematical simplicity. And therefore, blur invariants are defined as features invariant to convolution with some predefined set of PSFs or blurry kernels. And the choice of this set of admissible PSFs is important, so I will say something about it now. So first, it must be a set that is closed under convolution. Otherwise, the construction of the invariants wouldn't make sense. And second, it should contain all the PSFs that we are likely going to encounter in our task, but not much more. Because otherwise, the blur equivalent classes, whose elements are not possible to distinguish by the invariants, would be greater, and therefore the recognition power would be smaller. The most common example of such a set are PSFs or functions with n-fold rotation symmetry. N-fold rotation symmetry means that if we rotate the function by 2p over n, then we get the same function. And this is very realistic, for instance, in autofocus blur, as the aperture of cameras consists of number of blades, as is illustrated here. And therefore, the corresponding PSF roughly has this n-fold rotation symmetry. For instance, n2-fold rotation symmetry is called centrosymmetry, and it can capture even other scenarios like linear motion blur. And very special case is n1-fold rotation symmetry, which means that there is no constraint at all. I will get to this at the end. So, as I said, the paper, the article generalizes this theory of blur invariance to color images. So, let's suppose we have an RGB representation. The basic assumption that we have for application of invariance that we're presenting is that all three channels are blurred by the same PSF, which is illustrated here. And it turns out that this is mostly a realistic assumption. There might be little differences among them, but usually not significant. We tested that by photographing a single pixel on the screen with autofocus blur and comparing to PSFs. Well, anyway, the invariants until now were computed either on grayscale images or on individual channels. And the main contribution of our article are invariants, blur invariants that employ linkage between the channels. We call them cross-channel invariants, and they can be used along the old ones that are computed on the channels individually. And they greatly improve their recognition power and have many other benefits. I will get to some of them at the end of the presentation. So let's have a look at the definition. I will briefly explain. So in the definition, the capital F denotes the Fourier transform The indices J and K denote channels, and capital P is a projector on the chosen set of PSFs. And this set is the subspace of the set of all images. Therefore, we can have the projector. And to give you an idea about the projector P, if we consider the case of central symmetric PSFs, which is very common, then P might be the average of the original image with its 180 degrees rotation, which is stated here. Well, anyway, it's not difficult to prove that this term is invariant to convolution with any PSF from the chosen set of PSFs at all frequencies U where it is well defined. And the invariants with different indices J and K are the new cross-channel invariants. Just a practical remark, it's in fact not very convenient to work with the invariants in the spectral domain, as it brings severe numerical problems like dividing by small numbers, and it's not very stable. And since it's possible to derive a nice recurrent formula for moments of this invariant, we work with these moments that are also invariant. We don't have time to derive this recurrent formula, so I placed it here just for illustration, but the feature that we finally work with is a vector of real numbers. So from the many experiments that we presented in the paper, I will present here two template matching experiments that suit the moment well and also nicely demonstrate the recognition power of the new cross-channel invariants. So the setting is that we have a sharp image and a blurred image of the same scene. Then we take number of templates from the blurred image and we search for them in the sharp image. The assumption that we make is that we have the central symmetric PSFs, and the matching is performed as the minimum distance between patch features and template features along all possible patches in the sharp image. The features that we use are the moment invariants, but only up to the 5th order. The reason why we constrain the moment order is that 2 higher orders become numerically unstable. In the presentation, here I show you an example of one of the image pairs that we used in the experiment. It's a sharp version on the left and slightly blurred on the right. The blur is artificial with the uniform square as the kernel. And 100 square templates of the same size, 100 pixels, are selected from the blurred image. Just to give you an idea, I can now increase the blurring intensity a bit. Again, and this is the maximum blur that we use in the experiment of artificial blur. So in overall, we used 15 images of the same resolution, capturing various outdoor and indoor scenes. And in each pair, 100 templates were selected. Therefore, we have 1,500 templates in total. Okay, about the plot, on the x-axis, we have the kernel size going from 9 to 99, and on the y-axis, we have number of mismatches. We consider the result a mismatch if the detected position was more than half of the template size from the true position. So we compared the invariants to normalized cross correlation, computed both on grayscale and RGB image, as this is a standard technique for template matching. These are the black and yellow marks, and they ended up the worst. However, this is not so surprising because normalized cross correlation is a standard technique for this task, but it doesn't guarantee the robustness to blur. The red squares belong to invariants computed on grayscale images. The blue corresponds to blur invariants computed on channels individually. And finally, the green circles are the same as blue, however enriched by the new cross-channel invariants. And you can see that the improvement is quite significant. And maybe I should make one more note here that maybe you could expect from blur invariants that it should match everything perfectly because they are invariants. However, if we blur the whole image and then we extract the templates, we introduce so-called boundary effect, and no model can be invariant fully to boundary effect. But obviously it has some degree of robustness even to this. In the second template matching experiment, we replaced the synthetic blur by real blur made by a camera. To achieve that, we took 3 pairs of images. Each pair captured exactly the same scene with exactly the same setting of the camera, except for the aperture. The sharp one was taken with the highest f-stop, and the blurred one was taken with the lowest f-stop. And then we again selected 100 templates from each pair and matched for them. And as we are not able to modify the kernel size here anymore, because it's not artificial, it's real blur, we were looking at different template sizes. In general, most smaller template sizes are more difficult to match. And the results are very similar to the artificial blur. The green circles that represent the cross-channel invariants greatly improve the recognition power. Okay, to summarize, we came up with blur invariants that utilize cross-channel information of images, and they can be used along the old ones that are computed on channels individually. And the cross-channel invariants have 2 more significant advantages. First, it is possible to design them to any possible PSF unconstrained by anything. And this is not possible for a single channel version, and when we are not sure about the PSS we are going to encounter, this is a big advantage. And second, when single channel version is defined for n-fold symmetric sets, they are trivial for n-fold symmetric objects. For instance, some road signs and so on. There are probably examples you can think of. And the cross-channel invariants don't suffer by that. Okay, the last thing I want to say is that we almost finished a follow-up paper that is devoted to a more general case where we construct the invariants not only to blur, but also to linear channel mixing, expressible by matrix multiplication of the image channels. And practically, this channel bleeding can really practically happen due to several reasons such as imperfect filtering in the sensor. And we are planning to submit this follow-up article to transactions on image processing. That's probably all I wanted to say. Thank you.
Timing. Once again. And for questions. So I will ask.
So maybe you mentioned this, but I just missed it. You are using this 2 cross-channel variants,
yes.
And why you are not using all 3, or I don't know, maybe you mentioned it.
Yes, no, I didn't, and it's a very good question. The reason why I don't use, for instance, invariants that would bound R and B channels, red and blue, is that this invariant is dependent on the others. And it's dependent on the way, not that it would be dependent only on these 2, but we would have to use some of the 3 single channel ones. But if we use all of these, which we used in the experiments, then it is not efficient to use it because it's just a function of these.
So there is no reason to use different couples. If you would use, for example, red-green and red-blue instead of green-blue, for example.
Well, we can use any of these 2, but if we use 2 of these, then it's sufficient because the others are dependent. But we can use different pairs; it doesn't matter.
Yeah, I would like to ask, because if I understood well in your paper, you rely much on this theorem, or this Bayes theorem, and now you have also some assumption on distributed property of projector P. But in real cases, it could be violated, this assumption.
Which assumption?
About distributed property of this projector P, this
Oh,
Bayes
yeah.
theorem, yeah.
Yeah, well, the assumption about distributive property, well, it is satisfied, well, there is a theorem that it is satisfied if the projector is orthogonal and the set of PSFs is closed not only to convolution, but only to cross correlation.
Do you know any examples or practical examples that can be violated? This property?
Well, for instance, if we construct the P not this way, as like we choose this this definition of P because it is then orthogonal. But maybe like if you can think of a projector of a function to that would project it to the set of even function that is not orthogonal, then it is violated.
Wasn't the question that if you might have point spread functions that do not violate the conditions, the assumptions that you have on P? For example, if you have like a motion blur, a standard motion blur, which is not a linear, that it cannot be modeled by. I mean, it cannot be, any P cannot be used for an arbitrary motion model.
Yeah.
I'm just trying to, I think that was the question. If they are, I think it's a different slide, the slide where you show the different point spread function,
yes.
This one, yeah. So you might have point spread functions that simply cannot be expressed using the P. I mean, not expressing using the P, but there doesn't exist any P projector which can be used for these point spread functions.
I don't know if that's possible. If it's a set that is closed under convolution, then it's a subspace. Is it possible that there is no orthogonal projector?
I think if you have an arbitrary motion point spread function, which is nonlinear, then you don't have a projector operator for it. But maybe
could that be a subspace?
No, it won't.
Yes, well, that's the thing.
Because it's not going to be a subspace. Yes.
Yeah. Oh, that's the first condition, that it should be closed under convolution.
Since there are no other questions, then I thank you again, Ashik. And we will move to the last contestant, which is Marek Tyburec. And he will present his journal paper as well. And by that we will end this for. Do you want to use this? So please go ahead, start the timer.
Okay, so good morning everyone. My name is Marek Tyburec, and it's my great pleasure to present here my work on modular topology optimization for additive manufacturing of reusable mechanisms. This was a joint work with people from CTU, Martin Ruškář, Michal Sommer and Jan Zeman, and also with Martin Kružíky from UTIA. So as I mentioned, the title is about the talk is about topology optimization. So topology optimization is a method that searches for the most efficient distribution of limited amount of material within some prescribed domain, like 2D or 3D space, and we have some boundary conditions like forces, supports, and so on. But if we use topology optimization for these particular boundary conditions, we of course obtain designs like this one, that are very particular for that particularly efficient for the specific application, which on one sense is nice, but if we change the boundary conditions, then the resulting structure may not be useful. And for example, if you would like to dive into this sustainability aspect, I would like to, for example, reuse the structure after the end of the life cycle, then we cannot do it because the structure is not designed for that. From the other perspective, we may have structures that are made of repeated components, repeated periodic components, like what is in this figure. And these structures, of course, have this repeatability thing, so that maybe we can reuse them for something else. But the issue is that we lose performance for the original objective. So what is the subject of this talk is optimization of modular structures. So we would like to stay somewhere in between these two extreme cases. We would like to have structures that are made of a limited number of repeated blocks, which we call modules. But at the same time, we would like to be somehow structurally efficient. So that's the goal. And so within this setting, there are essentially two main questions. So what should be the design of the modules, like topologically, how should they look like? And the other question is, how should we distribute them within the domain to actually assemble something meaningful, like a structure that is able to do something. So that's actually the subject of this talk. We were talking about this modular topology optimization, then we will also somehow cover some slight improvements to actually allow for practical manufacturing of the outputs, and show an experimental validation, and then I will summarize. So within this presentation, I will actually showcase everything on these two examples. We have two structures here. Those are compliant mechanisms. So on the left, it's like a gripper mechanism that is fixed here and here. We have a force that is pushing to the right, and the goal is that these jaws should somehow close. So it's like a scissors somehow. And the second mechanism is a force inverter mechanism. Again, these points are fixed. We have a force pushing to the right, and now that right point should move to the left. So those are the mechanisms we would like to design, and we would like to design them using modules that will be shared among these two mechanisms. So that's the setting. And the strategy that we use here is a sequential strategy. It's kind of heuristic strategy because the problem is two-level and both levels are non-convex. So so far we did not succeed in having like a better approach. So we have a heuristic one here, and it's a three-step procedure. The first step is based on free material optimization, which somehow looks at the problem from the perspective of average response of the module types, let's say. I will talk about it in a few slides. Second step is to cluster these elasticity tensors to find out what should be the distribution of the modules. And the last step is then finding optimized designs that are made of these shared modules. So now let's start with this step one, which is free material optimization. So essentially the problem that we are solving here can be formalized in this way. So we are minimizing or optimizing performance objective, which in our case is a linear function of displacements. So essentially we want the mechanisms to be as efficient as possible in the sense that they produce the maximum output displacement. They perform the best action in the sense of what we have shown here. So that's the objective function. These displacements solve the elastic equilibrium. We have some resource constraint, which is described using the trace of the elasticity tensors E. And then we have some eigenvalue constraint on the elasticity tensors. So if we do this and solve such problem, like without any modularity, of course, we obtain solution that may look like this. this. And so what you can see here are the traces of these elasticity tensors, because of course these tensors have more components. I just visualize traces here. Okay, and then the idea is actually, okay, we have some distribution of these elastic properties, but maybe we can assume that if some tensors are similar, they should be realized by the same module type. So that's essentially the idea of this heuristic. So we developed a clustering algorithm, which is a simple hierarchical agglomerative clustering, where we essentially iteratively merge the nearest elasticity tensors. Where by this nearest I mean nearest in this Frobenius norm of the tensors. And so if we do this, we can control the final number of modules that will appear in the design. Of course, we don't go to this number 1 because that would not make sense. I'm just showing that it can go to the number 1. We also have some extensions here to account for symmetries, like structural symmetries or anti-symmetries. So for example, we can account for the modules to be able to be flipped, something like this. Right, and once we do this, we end up with an assembly plan, so distribution of individual module types in these two mechanisms, and we can just apply standard topology optimization to find the topologies of these modules. So essentially this topology optimization searches for an indicator function that describes what is material and what is not. And to solve it, we need to relax. This relaxation means that we relax this indicator function or these integer variables d into this 0-1 range. And of course that would mean that we would end up with designs that are not well separated, something that is not a material, not a void. So what we do, we introduce a penalization for this for the stiffness, and somehow this penalization looks like this. It's a standard thing, and by introducing this penalization for intermediate values, we end up with design that is mostly well separated, not entirely. Then we add some regularization to solve to the problem, to have mesh in the to have mesh independent designs after refinement, and some numerical issues. And we add also some simple projection scheme to account for the modularity. And compared to the non-modular setting, this setting is faster to solve. Okay, so that's the basic idea, and now some refinement that we did to that as well, or improvements. The first thing is we really want to be sure that we end up with something that is clearly separated, material and void. So for that we incorporate the Heaviside projection scheme, and actually we use this kind of function that approximates the Heaviside function. It's controlled by two parameters, beta and eta. Beta is a parameter that somehow controls how near are we to the Heaviside function. Like if this beta goes to infinity, then we have exactly the Heaviside function. And this eta is a value that controls where is the change of the value from 0 to 1. And illustration is here. So if this was the design field, then for value 0.25 you will get this kind of area of the material. For different values we get actually 0.5 we get a narrower space, and for value somehow it stopped responding.
I think just wait.
I have to wait. Yeah. No, so I will just continue. So if we increase this theta, it will again shrink the space. And why do I show this? Is that actually when we would like to manufacture this kind of mechanism, for example, using 3D printing. For example, using 3D printing. Okay. Yeah. Yeah. When we want to manufacture it, for example, using 3D printing, we cannot actually manufacture these designs exactly. So there will be some issues with tolerance and so on. So to handle this, we actually solve this kind of problem instead. So we solve a min-max problem when we solve over the worst case of different projections, meaning these different values of this parameter eta. And by doing this, we think, we hope to obtain something that is robust under manufacturing intolerances. Because these values eta essentially shrink or erode or thin the individual components in the design. Okay? And the last bit here for the manufacturing part, we want to ensure that each of the module is actually a single piece of material, so it does not contain like two components. We want to be able to pick the module and place it somewhere. And so for that, we built a graph of the finite element discretization. And actually the idea is looking at the Laplacian matrix of that graph. Because eigenvalues of that Laplacian matrix somehow tell us something about the connectivity. In this case, it's somewhat more involved, but essentially we have this kind of eigenvalue problem, and if the second eigenvalue is greater than some threshold, which is due to the penalization somehow, then we can control the number of components that we obtain in each module. Okay, now using this procedure, we optimize these Ripper and inverter mechanisms using a set of 8 modules that were reused between both these mechanisms. And you can see a short animation here, how one presses the mechanisms, and you can check actually that you can see that this point somehow moves to the right and left, and here that this point moves upwards. So you can see that it's somehow working. Of course, this is not the actual experiment, but for the actual experiment, I just have the data here. And I think the most important is that graph here. So when we measure the output to input, relation for each of the mechanisms, and these horizontal lines here indicate the performance of these thinned, thickened, and intermediate designs. The intermediate design is of course the one that we manufactured or try to manufacture, and then we have three samples that we 3D printed. Those all of them corresponded to this intermediate field, but of course because of some manufacturing issues, because it's not always 100% reproducible, we see some response that is not always the same, but we somehow somehow satisfy what we predicted from the optimization. So I think this is almost it. So just to summarize this talk, so what is the contribution that we did here is optimization of modular structures where the modules are reused among multiple compliant mechanisms. So this is something that has not been done before. And for that we used a sequential procedure. The first step was based on free material optimization, which provided us with distribution of elasticity tensors. Then the idea was to cluster them based on the similarity metric of these tensors. And the final point was using the cluster design, we used topology optimization to find how the modules should look like. And essentially that's it. So thank you for your attention, and I'm happy to answer questions.
Thank you, Marek, for your talk. And yes, please. So, go ahead and ask us.
I got feeling that you mentioned that seal approach is suitable for description of self-assembly properties. Is it so, of material?
Not entirely self-assembly. I mean, for self-assembly, there were some related things in self-assembly direction in the group at CTU, but it might be somehow in the future useful. But currently, there is nothing about self-assembly.
because in fact there is some, let's say, direct connection with your approach and so assembly properties, but it comes from, let's say, physics or materials, while you are optimizing it.
Yes.
It could be.
On page, I think, 12, you use something you call three-field heaviside projection. So I wonder what is it? Is it some kind of standard technique, or
yeah, so
where
this
it
is,
comes from?
Yeah, this is actually kind of 10 years old, I would say. Yeah, but it's standard. This is something that is standard in topology optimization right now to account for these manufacturing intolerances. Yeah. So and how does it come into play? So let's try to explain. Yeah. So we have
Heaviside. It's a name or a person?
Heaviside, actually, heaviside function, that's a step function, yeah. That's the step function. And we only use like approximation of that because, of course, when you optimize, we need a function to be differentiable somehow. So we have function that is differentiable, that one, and with that we approximate somehow the step function. And yes, so it comes from that.
Actually, at some figures I can see that the resulting structure is not continuous, that there are some isolated.
Yes.
So what is the reason for that?
Yeah, so the reason is essentially the heuristics that we used. Yeah, that's the heuristic that we used here, somehow to provide us with an assembly. And there are more reasons actually for that. First thing is for this free material optimization problem, this is a relaxation actually, this is a relaxed setting. And the tensors that we obtain here may not be actually realizable by the materials we have. So we have a broader space. We don't care because it's a heuristic somehow, but we may be outside of this realizable space. We do the clustering, and then we may obtain something, I don't have a figure here, but we may obtain like regions here that may be used for a purpose that's, for which we cannot design the modules, for example. So that might be a partial reason why we get this. The second reason is that solving this topology optimization problem is quite challenging. It's a non-convex problem, and if we enforce modularity, somehow we somehow introduce this kind of combinatorial nature into the problem in some sense that it's more challenging to solve. It gets more local solutions. So that's why I actually did not mention it here, but I have it on this slide, initialized with the results of step 2. So we have a starting point that we use for this optimization. Because if we do not do this, we obtain something that is typically not working so well. Yeah. I mean, these isolated components, for example, in this case, these ones, I think these ones, for example, are not structurally important, so they don't influence the response of the structure, but yeah, they appear in this case, and that's because of the distribution of the module types.
Well, I have one quick question, maybe. Well, it's so quick. But I wonder if you have considered, because looking at this problem and just seeing these modules, and that you are trying to find out their structure, and you're using this heaviside, and basically you want a binary mask telling you which voxel is a material, which one is void. I wonder if one couldn't use something similar what Tomcha was using in her problem, and you have an optimization problem, but you represent your image, in your case, your module, that you represented by a neural network. And there are these nerves, they are called nerves, those are neural random fields. Yeah, neural random fields they are called. And they are used to represent 3D objects. And they have some nice properties. They have these inherent sort of priors which are encoded in their architecture. And this may be something what you might consider in the future. to try to use, because you would just keep your optimization problem, and you, instead of optimizing with respect to voxels, you would optimize with respect to your parameters of the neural network. Maybe someone has been doing that, I don't know, in your field, but if not, then I guess could be a...
I know that there were some trials with neural networks, but so far no like really conclusive result to say, okay, this is like good. But I'm not saying that this is the idea that you mentioned.
Yeah.
I don't know. I don't have experience with it.
Yeah. Okay. Fine. So thank you, Mike, for your talk and for answering the questions. Now we will ask everyone in this room, from the audience, to leave and let the committee to decide. And please come back. So what do you think? In half an hour we should be able to announce the results. So we will be more than happy if you come in half an hour and we will announce the results of this competition. And those who are online, I will now turn off our audio microphone. Are you there, by the way, Marco and Marwan?
Yes, I'm listening.
Yeah. Okay, fine. So, I mean, you can stay online. I will just turn off the microphone. Yeah, you did. Jo.
Oni tady
No
vlastně
jo.
nebudou. No, takže.
To nevadí. Jo, ne, tak dá se to udělat takhle. A je tam... To udělám já sám, myslím. Jo, už to dělám. To by byl hodně velký vzadu. Jenom ještě potvrďte mi, že mě slyšíte, Marko.
Jo, slyším.
Slyším, Amarovan, can you hear us? Just
yes.
Okay, perfect. Yeah, we have to wait a couple of more, maybe hopefully only seconds, before Ms. Pilhapa brings the diplomas. She's printing them out and it takes time.
Já vím, že čísla to na schůl a musí to být zkoumat. Ona měla všechno varianty. Jo, takhle, ale jako to pořím se tam jsou. Já jsem si přišla, jako jestli měla všechny varianty, že měla jako všechny na první místě, druhý místě, třetí místě. Ne, to ne.
Já to tady vezmu X tam. Extra práce. Připravit. Já jako děkuju vám v komise, že jste se účastnili o jiném počtu, jsme tady byli vlastně v plném počtu, protože minulý rok a myslím, že ani předminulý rok jsme tady nebyli úplně všichni, tak to bylo krásné, že jsme se zrovna shodli na jednom datu, co budou mohli všichni. Nevím, jakým způsobem zvýšit množství článků, který se tady objevovaly. Já myslím, že to není problém toho, že vlastně není kdo by to posílal, ty články do té soutěže v zásadě. To je trošku... No, tak na jednu stranu nedokážu si moc představit, že bychom zvládli toho víc teda. To bylo asi od zástav člověk. A to bylo jenom 15 minut. No, kdyby bylo víc, tak bychom museli skladit ještě. A už. Tak,
Čili to bývalo celý den.
no tak.
Já myslím, že jestli jsme chtěli kolik času měli.
Yeah. So much for the second. I will again switch to English so Marwan can understand what's going on here. Thank you all the contestants for attending this competition and also for giving us really a hard time to rank you, because all the presentations were very good. The committee has agreed that they were really all even, and also the publications, the journal publications are quite good, really outstanding, some of them, and so it was very hard to decide who should be first, who second, and etc. But unfortunately, we have to make certain ranking, and so the committee has then decided that we will give an award to the 3 best contestants. And if I start from the end, so on the 3rd place, we will give the award to Antonio Bourgeois. So congratulations. Once again first, but I'm sure that next year you will be the first. Okay, congratulations.
Congratulations.
Okay, so and on the 2nd and here it was even more tight. So we were not really able to decide who will be the first and who will be the second. So we have decided that we will give this award to 2 people. So there will be like a 1st and 2nd place, and that both belongs to Marko Lumen and Marek Tiburec. So Marek Tiburec is here. Congratulations. Marko,
Thank you very much.
Please turn on your camera so we can see you, because we are going to take a picture of you as well. Unfortunately, we cannot give you the diploma, but we will hold it. I mean, no, they will hold it, and we will take a picture of you. Come, both of you. I mean, here. And I take a picture of you in front of Marko. And hold it there for him. Like that. Excellent. Nice. Yeah. And I just take a picture of both of 3 of you. And yeah, you can get closer. Okay, fine. Okay. Once again. Thank you. So once again, congratulations. Okay, so that's all for today, and I hope we will see each other on a similar occasion in 1 year, and hopefully we will have maybe more journal papers, more contestants, and if not, then at least we will have hopefully the same number. So thanks again also to the members of the committee for spending the time here and giving their advice. Thanks a lot.